Okay, well, I'm just gonna record it anyway because I can't figure out my camera, and I sure as hell can't figure out most of the things in my life. I guess I'm just gonna be scrolling. You're not gonna be able to see me all at once, all the time. It's gonna be like one of those old TVs with the icon that bounces around, and you hope it gets into the corner. Because I can't figure this out. So as the video title lets the viewer know, want to talk about London Dispersion Forces and how they relate to orbitals, because I literally, like, I just look up like London dispersion modeling because I'm like interested in a specific interaction between p orbitals, and I can't find it. You can't just YouTube something like that. So this video is going to be talking to you about how London dispersion forces generate photons, one, and two, what is actually happening when you get London dispersion forces to a very simple atom. We're going to be talking about helium today. Helium, and I keep saying helium because I really don't want to say hydrogen, because I'm going to see it and I'm going to want to say hydrogen. And if I say hydrogen, you go ahead and you comment and you say, hey Elias, you said hydrogen instead of helium, and you're supposed to say helium. And now that that's over, we can go ahead and proceed. So I went and stole this beautiful image from the interweb, and I took it, and then I was like, all right, cool, I'm gonna go ahead and throw that in some cool art. So I did that. I threw it in art, and I was like, whoa, all right, sweet. Now maybe I can steal the s orbital, because I'm only gonna be talking about helium today, no hydrogen. And we are going to be talking about what happens when you cool helium. So in the present state of how we're going to have this discussion, you're going to have some we're going to have shared presumptions. One is that this helium is very cold, and the reason I say that is because we don't want any of those photons of higher energy, of maximal energy, impacting our helium atoms, keeping them not interested in interacting with each other. So we're saying that, okay, we've either increased pressure to a limit on this helium where it's now interacting through London dispersion forces and they're able to get into that resonance, or that we've supercooled it, which is inherently like we've dropped the pressure. Um, but regardless, we've extracted the extra photons that allow the helium atoms individually to escape the London dispersion force. So let's talk about it. Okay, so we have the s orbital, and that's all that we care about today, but we do have orbitals that come in different flavors or different types. We have the p orbitals, which you can think of as linear orbitals because they operate in the dimension of forward and back, or up and down, or left or right. These are our first movement away from perfect point geometry, which is the s orbital. Then you can also think of, if we take the same paradigm and we apply it to the d orbitals, well, d orbital is a plane. And you can see that very easily when you look at the four surfaces here in d sub minus 2. It's a flat plane in the xy domain. Then you can see that it's the same flat plane in the one next to it, and the other two on the far right. Now you see something really interesting happen in the middle one, where you get this little disk in the middle. And the way I like to imagine that is that the plane itself exists in the middle. The way that the d orbitals and the f orbitals and even the p orbitals are defined is by their nodal points. And you'll see here that we have one nodal point, and it's a division point between the actual orbitals themselves. The p's have a single node, while the s has 0, obviously, and the d's have 2 nodal points, and the f's have 3 nodal points. That has nothing to do with London dispersion forces. Just thought it was really cool. Had the opportunity to talk to you about it. So I digress. Moving on, okay, we are going to talk about the simple s orbitals. Okay, so now we're going to go ahead and remove all of the atoms from the universe besides 2 helium atoms, because, you know, when talking about a very specific force, we're going to have to do that sometimes, because then there's the headache of, well, isn't that this or isn't that this? I want you to know that I'm talking about something very specific here. So we have two helium atoms, not hydrogen atoms, that are right next to each other. And let's say there's some sort of attraction, and for this instance we're really concerned about the electromagnetic force, because as we'll see, that is what is the root of the London Dispersion Force. Now we've extracted all the photons. There's nothing keeping them apart in the frequency of light that would keep them from not interacting within the London dispersion limit, which we'll start talking about. So there's this distance which I've kind of put here as delta, or capital delta, and that distance is decreasing. I didn't go ahead and draw it because I'm too lazy to draw the second one, but as you can see, as helium 2, which we'll call this one 2, the ones will be on the left, as helium 2 starts to accelerate, and I use the term accelerate in the direction, not just move in the direction. I mean accelerate, because it's an acceleration. As it accelerates towards helium 1, helium 2 and helium 1 will have a simultaneous deformation of their electron orbital. What's happening is that the negative charges of the electrons in these orbitals are displacing themselves in space across the actual center point, which I have here in this gray line as the original center point for the perfectly spherical s orbital. The center of mass remains generally the same of the atom, while the electron orbital displaces or disperses across the surface of the atom. I'm getting a little caught on the terminology here, but what I really want you to get from this is that the center of mass kind of remains the same, because the majority of the mass is in the center of the atom itself. Now, as the atom continues, or helium-2 continues to accelerate and gets really close, it's going to reach a terminal distance, because then you have fusion, and we're not talking about fusion here because we're talking about London Dispersion Forces, for heck's sake. Anyway, let's say it reaches that terminal distance, and I've shown that terminal distance here. It's some arbitrary distance, and obviously there will be some, it's not going to be perfectly where they reach that distance and stop. They will obviously oscillate a little bit in that range, but I'm saying they've reached equilibrium. They're right next to each other, and what you'll see is this oscillation back and forth across this line, which brings me to my next image, which will be light, baby. Okay, so I told you that London dispersion forces are going to allow light waves to propagate through them, and the way that occurs is light is an oscillation in the electromagnetic field. So as you have this electric field oscillating in one direction, which will say most of the negative charges on this side of the center of mass, and then oscillates to this side, and then oscillates to this side, then oscillates to this side, you'll start to see to a 90-degree level, an oscillation in the magnetic field, and that's how you get oscillations in the electromagnetic field. Now, the rate of that oscillation is what gives you your frequency, and the distance between trough and trough, or peak and peak, is your wavelength. We know that the speed of light is constant, and the way the amount of distance required for these oscillations to propagate through space is the speed of light. So then we can go ahead and reason out, given the wavelength or the frequency of that oscillation, we can get the wavelength, and et cetera, et cetera, et cetera. So my question, the whole reason I made this video, out of frustration with the fact that the videos don't exist, is which direction in relation to the resonance is the emission? Like, so if my electric charge is oscillating, let's say, up and down, up and down, up and down, I would think that you would get a magnetic wave that's coming towards me and away from me and towards me and away from me from your image. But then you have to think about it too of in actual space. If I have a sphere and that sphere is elongating in this direction, it's pushing space-time in that direction and then back in this direction. So the actual electromagnetic wave is oscillating this way, outward. So I'm kind of unsure of that. So these are my questions regarding the van der Waals or London Dispersion Forces. Uh, these forces are really important when we start talking about oils or larger molecules. I started talking about it uh, while I was reading the book What is Life by Erwin Schrödinger. Really interested in it. You should check it out. That's all I got for you. Hope my question was intriguing for the most part. I hope you learned something if you didn't know something. And if I look like an idiot, go ahead and smash that super like button. Like button. This isn't Tinder.